Hello, everyone. Welcome to the Internet of Senses podcast. My name is Tyler Heaton. I am a sound designer and researcher in the Spatial Technologies Applied Research and Training Center at Lethbridge College, where I specialize in the implementation of spatial media and technology in immersive experience design. The Internet of Senses podcast is a series of podcasts with experts in various fields that focus on our five senses. The Hearing Series is an opportunity to explore how we process auditory signals and the amazing research and technology that is being developed in the world of sound and hearing. Today, we are joined by Dr. Julia Campbell to talk about auditory processing, brain plasticity, and the neuroscience of hearing. Julia Campbell obtained a clinical doctorate of audiology and triple research doctorate in speech, language, and hearing sciences, cognitive neuroscience, and behavioral neuroscience from the University of Colorado at Boulder. Currently, she is a clinical associate professor in the Department of Speech, Language, and Hearing Science at the University of Texas at Austin, where she serves as the audiology program director and principal investigator of the Central Sensory Processes Laboratory. Julia also serves as the chair of the scientific advisory board for the Misophonia Research Foundation. Julia's research interests are focused on the identification of an objective measure of tinnitus using EEG, and she has published on this and related topics in the American Journal of Audiology, Journal of Speech, Language, and Hearing Research, and the Journal of American Academy of Audiology, among others. Julia, thank you for joining us today.
Pleasure.
So I've been really excited for this one to talk about neuroscience as it relates to hearing and audio processing. This is, a really science-heavy topic, and I say science-heavy in a good way. I think that it's really great for us to understand that science of hearing and audio processing and how that works. And we'll use that as a bit of a jumping off point for the conversation today. So to set some groundwork and provide some groundwork for our audience, can you give us a brief explanation of auditory processing in the brain? Kind of like the cocktail party overview of how hearing and audio processing works.
Sure. I guess I would start at the beginning, and that's the fact that all sound are pressure waves through the atmosphere, and those pressure waves reach your eardrum or your tympanic membrane, and that causes your tympanic membrane to move. And then that in turn causes your ossicles or the bones in your middle ear space to vibrate in a very complex manner. And that then causes fluid movement in the cochlea or the inner part of the ear, which sets off a cascade of neurotransmitters and eventually action potentials that activate the eighth nerve, the hearing nerve. And that nerve then connects to the brainstem and goes through several hubs in the brainstem up through the thalamus, which is known as the gatekeeper to the cortex part of the brain, which is the highest centers of processing in the brain. And so then sound reaches your primary auditory cortex, which is the first stop in the cortex. And from there, connects to secondary auditory cortex, frontal cortex, prefrontal, all different areas throughout the brain. It's best to think of it as a network, like a motherboard, rather than this area is dedicated to auditory processing, because there's a lot of interaction, as we'll talk about later, with different sensory systems as well throughout these areas. And so that's how sound gets to the brain. It's really an interaction between excitation of the nervous system, but also inhibition. And inhibition or suppression of neural activity is really how our central nervous system works. It fine-tunes excitatory activation. It provides a balance to the nervous system and the different firing rates and synchronies that we see. And so this interaction, again, we'll probably talk about it later, but it's very key to having a balanced nervous system and being able to process sound accurately. And probably the last general thing I'd say about auditory processing is it's very temporally regulated. And so that means timing. we're very, very tuned, I would say exquisitely, to the timing, and that's how we process sound. Whereas, to kind of give a contrast, the visual system is very spatial, very 3D, location oriented. And so, again, these two systems are heavily intertwined to be complementary to one another.
That's very interesting. I'm glad that you mentioned the timing side, or the temporal nature of sound, because I think a lot
Mhm.
of people we don't think about that, but it's
Right.
quite an interesting part when you start looking at things like ILD and that kind of
Hmm.
stuff. And well,
Hmm.
I guess not ILD, but ITD.
Right.
Uh,
Both of those.
yeah,
Yes.
both of those, and how they relate to localization, which is
Hmm.
uh, sort of one of my areas of research.
Hmm.
So, what was it that interested you in hearing and speech? Did you start with hearing and speech and
Hmm.
go into a sort of a neuroscience side of it, or did you start with neuroscience and go into hearing and speech?
That's a really kind of bizarre story. I wanted to be an astronaut, and clearly that was not meant to be. So I started out with engineering and tried to do aerospace engineering, and that was not my natural talent, to say the least. And so I ended up going to psychology. My mom and my sister had both done that with great success, and so I thought that that was probably where I had a better fit. And I went through the psychology program rather quickly and was not sure where to go from there. I didn't want to counsel people for my career. That wasn't my inclination. But I missed the math side. I missed the engineering side of things, learning how things work, troubleshooting. I really have always enjoyed troubleshooting things. And so my mom actually had a client who was an audiologist, and she said, "Have you ever heard of this career path?" And I said, "No, what does that mean?" And so I ended up on a leap of faith taking a bunch of leveling courses in audiology my senior year of college and really enjoyed it. It was a good mix of the psychology of hearing, the perception of sound, but also, the hearing science of it, which is very technical. And so I was accepted to the audiology program at University of Colorado. And into my second year of the 4-year program, I started to wonder maybe this wasn't for me. I wasn't sure if I could see myself doing hearing testing as my main focus or working with hearing aids. And at that time, our department was interviewing candidates for a faculty position, and Dr. Anu Sharma interviewed. And it was the first time I had really heard a researcher give a presentation that I fully understood, and I enjoyed it, and I felt very excited, and I hadn't felt that way in a while about, my career path. And so I met with her and asked if I could work in her lab and help her set it up when she accepted the position. And she was just really wonderful and encouraging and had me working on a paper. And I did not want to get my PhD. I was adamant. I do not want to do this. I don't want to write a dissertation. I don't want to be in school for another 10 years. But I really enjoyed working on this research paper, which ended up being my first publication. And she had a student that ended up being also a faculty member at University of Colorado, Philip Gilly. And he was my mentor. And he also said, "Well, have you thought about, doing a PhD or whatnot?" And I said, "I just don't know if I can do it." Anyway, long story short, they started to convince me. And so I applied to do the AUD audiology slash PhD program. And, working in the lab, doing EEG, working with children and cortical development, I really felt like I needed to take extra coursework to understand the fundamentals of what I was doing. And so that's what got me into the track of neuroscience, and taking those courses was kind of this desire to really have a better fundamental understanding of what is EEG, what is it measuring, what is it good for, what is it not appropriate for, and that's kind of how it happened.
Just sort of fell into it at the right place at the right time.
Yeah, it was definitely a God thing for me.
Yeah. Nice. I'm glad that you brought up EEG because we'll talk about that in a little bit. I think that's a really interesting technology and tool and way to understand what's going on in the brain. Before we do that, I just want to talk a little bit about the Central Sensory Processes Lab. That sounds like a really interesting place to be doing research. And you're a principal investigator there. Can you tell us a little bit about the lab and what kind of work you're doing there now?
Absolutely. So the name is a mouthful, but the reason I chose that name is because I didn't want it to be an auditory lab. I've done a lot of work in the visual system as well. And I have a great colleague, Garrett Carden. He's in Utah, and he has done a lot of work in the somatosensory system. And so I wanted it to be a lab that was open to all sensory studies. So that was why we chose the sensory part. And then the central part is because that's where, and this is my bias, that's where I think the magic happens in the system, is really the brainstem and the cortex. And so I wanted to give myself the freedom to investigate different modalities of sensory processing and how those modalities interconnect. So that's kind of how the lab came to be. Always my first love in neuroscience has been the mystery of tinnitus, or ringing in the ears, or hearing sounds that are not externally present. That's always fascinated me. So that's where I pivoted after I graduated with my degrees. Was I turned to tinnitus because I've always, it's kind of like the Wild West a little bit. We've done so much in research for that disorder and come so far, but the clinical aspect has remained stagnant for years. And how we test for this disorder, how we help to provide intervention, it just hasn't moved. And so that's really been the focus of the lab. But we are also very interested in visual processing, looking at inhibition and how that applies to sound in both clinical and typical populations. I love studying development and working with children and seeing how their brains adapt and why they adapt in certain ways and maybe not others. So our lab is very open. I would say our focus right now is on tinnitus, but we have side projects as well.
It sounds as if any deep study of one sense ultimately ties into a
Yes.
study of another sense. Like there's
Yes.
not really a way to disconnect them. And so that, as you're saying, that central
Exactly.
processing aspect of it is so integral to the study of all the senses, which, you know, kind of is the idea around the Internet of Senses podcast series as
Right.
well. Is that there's this connection
Right.
between all senses, and by bringing different people together, we can start to learn about those
Exactly.
connections.
Exactly. I mean, how we operate in the world, sensory wise, is astounding. I remember hearing a quote from a very accomplished neuroscientist who said that the more he learned and the older he got, he couldn't believe that we could get up and walk across the room because all that has to work together is just crazy. But when we do these experiments, everything is so titrated and specific to, unimodal processing and whatnot, which is necessary to understand things at an initial level. But really, to me, the interesting thing is, as you said, everything ties together. If we're looking at auditory function, it doesn't happen alone. Again, the visual system is so complementary to it, so it's difficult to separate those things.
You've done some research in cross-modal recruitment and
Mhm.
reorganization.
Mhm.
How How does that occur? Is that
Mhm.
something that naturally occurs at a certain level, and then we see it occurring more with different types of sensory impairment, or in
Mhm.
people not having access to certain senses, you see more of that cross-modal functionality?
Mhm. That's a great question. So it depends on when the sensory loss occurs. If a child is born without hearing, we call that congenital deafness, profound deafness. We start hearing in the womb. So they don't have a hearing loss at birth. They've had a hearing loss of several months in the womb as well, which we also think affects how the brain begins to develop. But that's a very difficult thing to test, as you can imagine. But for a child who hasn't heard, the cortex of the auditory system is not going to have received stimulation or input. And so instead of letting those neurons or that network go unused and completely prune it away, visual neurons in that same area will start to recruit and take over that area to help in processing. And we showed this in a study looking at children who received cochlear implants, and they had activation in the auditory cortex when they watched a visual stimulus, whereas children with normal hearing didn't. They only had activation in the visual cortex. And so we do believe that is a compensatory mechanism to help process sound related communication, but visually. So things like lip reading, being able to orient yourself very quickly to different spatial locations. One of the best studies on visual cross-modal recruitment was done by Steve Lomber and colleagues. And what they did was they had deaf cats and they had them do a visual task. And it was basically peripheral localization. Okay. And so the deaf cats, compared to hearing cats, were able to localize at the extreme periphery much better, all right, than the hearing cats could. And so the theory was maybe they had recruited parts of auditory cortex to provide this enhanced visual behavior. But to test that, they needed to be able to deactivate the auditory cortex somehow. So they implanted these cooling loops that would cool the auditory cortex without harming it, and it would be deactivated. And so then they re-presented this visual task, and they found that the peripheral enhancement went away, okay, when they deactivated auditory cortex. When they let it warm back up again and redid the visual task again a third time, that enhancement returned. And so, as you can imagine, for survival, if we go back to that kind of primitive question, if you can't hear, your visual system needs to be on high alert for processing purposes to alert you to danger. And so that's in the case of, a developing brain. If you've heard throughout your life and you have those networks established and then you lose your hearing, we still see evidence of visual activation of auditory cortex. We still see that, but it's most likely a different mechanism. We think it might be something called unmasking of visual networks that are already in auditory cortex. And so they'll kind of rise to the occasion. But we also see that reverse or is reversible with hearing aids and sometimes cochlear implants. And so you can do pre and post studies where you look at, is recruitment present, i.e., is auditory cortex responding to visual input? And then you can fit a hearing aid or a cochlear implant and then redo the task a few months later, and it might go away. So we do think it's more of a different mechanism than a hardwired mechanism that might take place early in development with sensory deprivation.
It's very interesting. That brings me back to one of the questions I have about the study that you did around single side deafness
Mm-hmm.
with the pre and post cochlear implant,
Mm-hmm.
and noticing the changes there. You were doing it in children, so it was developing brain
Mm-hmm.
versus work that you've done later on with hearing loss with adults. How important is intervention or changes to a developing brain versus an older
Mm-hmm.
patient or an older subject?
Mm-hmm.
And I imagine there's a lot of different things to consider there, of course,
Right.
because there's something else I want to ask about later around cognition. So how important is that early intervention with that sort of neuroplasticity?
Mm-hmm. That's a really good question. So with children, one of the main factors, and again, just like you said so accurately, there's many significant variables, but one of the main factors is the degree of hearing loss. So if they're born profoundly deaf, we do know that there's what we call a sensitive period where the brain kind of waits for sound to come along. And that seems to be maximum of 3.5 years. Dr. Sharma showed that we have to get sound into the brain for it to develop like someone with normal hearing. Some researchers are saying a year or less is more optimal if you want the child to perform like a typically hearing peer. Okay. Which is not necessary all the time.
Mhm.
Some people want to use sign language. Some people want to use total communication, which are all fabulous. But we've seen if the goal is to be purely oral and to have brain development similar to a typically hearing peer, then sound should be introduced within 3.5 years. And not only introduced, it's not enough to just give a hearing aid or a cochlear implant. It needs to have therapy, speech language therapy, right with it. That is a must. I have seen a couple children, that's been very, very difficult to see, who I don't know what the situation was, if it was the provider or the family, but they had a device and then there was no therapy with that, and they did not have oral language. So the therapy piece is just as important as the device itself, whatever that might be. If a child has some hearing, they are going to have some input or stimulation of the central nervous system. That's going to vary from child to child, but they're still going to need some type of amplification and speech language therapy. And this is all if the hearing loss is what we call prelingual, before language is learned.
Mhm.
If the hearing loss is postlingual as a child, they are still going to have a lot of neural networks in place. Okay. But they're still going to need speech language therapy, a device as they develop, because auditory cortex continues to develop into your 20s, which is pretty crazy.
Mhm.
So they're still going to need that stimulation or input. For adults who lose their hearing and have these auditory networks hardwired in place, the main factor then becomes how long is their hearing loss in place. That has been shown to be the best predictor of rehabilitation for sound in adults. So there was one review by Giraud who showed that in cochlear implanted adults who acquired hearing loss, that length of time showed how well they would perform post implant.
Very interesting. So it seems like there's a line sort of
Mm-hmm.
between that input side and that processing side,
Mm-hmm.
and there's technology interventions that are part of that input side, But then, as you're saying, there's that therapy that's about
Right.
how is that input being processed? And if the
Right.
correct input isn't
Right.
provided, the processing doesn't develop in a way that makes it beneficial to have that
Right.
that technology or that mechanical intervention.
Mm-hmm. Mm-hmm.
Yeah,
Yes,
very
that
interesting.
yeah, that therapy is really key for neuroplasticity to form those networks. We talk a lot about Hebbian learning, and that therapy is what really consolidates those networks together.
Very interesting. There's a couple of different directions we could go from this point,
Yeah,
but I want to give some time to your research with EEG and tinnitus,
sure.
because that's, as you've mentioned, that's something that really has fascinated you, and it's such an interesting area, as you say, like a frequency or a sound that has no external sort of
Right,
source, and
right.
yet we can hear it, and that's really fascinating. So can you talk a little bit about your research around tinnitus,
Yeah,
and then we can talk a bit about how you're using EEG to do that research?
yeah, of course. So there's many theories as to the neurophysiology of tinnitus and how it works. I would say right now, and this will change, but right now, the literature and the field seems to agree a bit that there's some sort of peripheral damage that is a trigger for this abnormal percept of sound. And so cochlear damage can be a lot of things. So that's damage to the inner ear. Typically, we think of cochlear damage as hearing loss, which is usually outer hair cell damage. That is a very old viewpoint of cochlear damage. So you can have cochlear damage without it showing up on a hearing test because a hearing test is only testing certain types of neural fibers and their firing. And so you can have damage to the inner hair cells of the cochlea, and we don't currently have a direct way to test that function. Well, we have a few outer hair cell measures. We have measures of the eighth nerve, but we don't have really good measures of inner hair cell firing. So it is possible to have hearing loss that your audiologist might not be able to pick up on unless they're doing other tests. So, other tests that can pick up on hearing loss are otoacoustic emissions, which test outer hair cell function and are more sensitive to subclinical hearing loss. Audiologists typically only test up to 8 kilohertz, and we hear up to 20 kilohertz. And so people are now starting to test those extended high frequencies more to see if there might be damage in that area, but there's no normative data. So we wouldn't be able to say for your age, oh, you have hearing loss here. It might be typical. So that's an interesting area. But all in all, we think there might be some sort of cochlear issue that is resulting in a lack of excitation to the central system. When we have that lack of excitation of neural firing, then what also happens is the inhibitory system does not fire or communicate as well because they're all interconnected. So you can
Mhm.
imagine you might have an excitatory neuron and there's inhibitory neurons connected to it. If that neuron stops receiving input, these guys are also going to stop firing, which then, if they innervate these other neurons that are excitatory, these guys will start being hyper excited because they can't be inhibited. So
Mhm.
that's how we get what's called the homeostasis of the system thrown out of balance. And without going into too much detail, if the homeostasis is thrown out of balance, that puts you at risk for things like tinnitus, hyperacusis, um, these atypical auditory sensations. So we really think it has to do with inhibition. So I had a mentor when I was hired at University of Texas. His name is Craig Champlin. He's a legend. He knew my interest in tinnitus, and he suggested to me, why don't you look at something called sensory gating in tinnitus? And I thought, oh, what's sensory gating? And so I did a deep dive, and it ends up that sensory gating is a EEG measure. It's a measure or tool that we think reflects something called sensory inhibition. So it is a measure of inhibition, a very specific type. There's a lot of types of inhibition, but this is a very specific type. It's pre-attentive, meaning you don't have control over it. It's an obligatory response. So we all have it. We don't know we're doing it. And it's really heavily studied in schizophrenia. That's where it really was developed as a tool or a measure of inhibition, and has been linked to auditory hallucinations in schizophrenia, and has been so heavily studied that it is thought of or considered to be an endophenotype of schizophrenia. And we know what genetics contribute to this mechanism. We know the networks, hippocampus, frontal, prefrontal cortex, all that. So it's really well understood, really, really well understood in neuropsychology, but had not been looked at in the realm of audiology or auditory neuroscience. And so I thought, well, if we think inhibition, we don't know what type, but in general, if inhibition might be an issue in tinnitus, maybe this tool or this measure could pick up on that. And so we decided to apply that to our lovely college student population who surprisingly were coming in reporting tinnitus and also seemed to have very normal hearing. So that raised the question of, if we're not picking up on a hearing or cochlear damage, doesn't mean it's not there. Could still be there, but they're at less risk for this peripheral inhibitory decrease being an issue. So maybe there's a central inhibitory problem, and sensory gating could reflect that. It's a very simple measure. It takes about 20 minutes. It's very clinical. You can have the patient read or watch a movie on mute. That's what we have them do because they can't fall asleep. They have to be awake. But we also don't want them paying attention to the sound because we know that affects this response. It needs to be completely subconscious. And so all it is two auditory stimuli that are the same, identical. They can be two tones. It can be two syllables. It can be two noise bursts. Clicks are heavily used in neuropsychology. And they just go, we use a tone. It goes beep, and then we wait 500 milliseconds, beep, and then we wait about 7 seconds, and that resets the system. And so you do this over a period of time. You average the brain's response to the first stimuli in the pair, and then you average the brain's response to the second stimuli in the pair. And if you're gating, you've heard the first stimulus, so the second one shouldn't be important to you because you've heard it. So we expect a suppression in the amplitude of the brain's response to that second stimulus. Okay, so it should be reduced. And if you have atypical gating, the responses to both stimuli might be the same, or the response to the second stimulus might be larger than the first. And so that reflects a lack of inhibition, a lack of the central nervous system's ability to suppress or filter non-novel or unwanted information. And so the theory goes that if somebody has poor gating, it could be that they're able then to perceive this internal auditory signal that is usually filtered out. So we definitely don't think this is going to be the mechanism for all tinnitus sufferers. It might be that some people have, due to genetics, have naturally great gating. And so when they get hearing loss, they don't develop tinnitus because they have a good gating system in place. But it could
Mhm.
also be the case that for those who do have tinnitus, their gating system isn't great. And so when they get hearing loss, they're naturally inclined to develop tinnitus. We have shown this to be a mechanism in adults with normal hearing. Our work has been corroborated by another group in West Virginia. Kenneth Morse, and his group have shown very similar findings to ours. And so now the next step is to look at this mechanism when hearing loss is present, as well as tinnitus, because those two variables are going to interact on the gating response. But hopefully, if our findings hold, at least in a subgroup of tinnitus sufferers, we might have a way to diagnose that percept.
Mhm. That's really interesting. So tinnitus, still a lot of times the root cause is some sort of hearing
Mm-hmm.
damage or trauma.
Mm-hmm.
But what your research is suggesting, the theory is that it's a mechanism related to that filter, that
Mm-hmm.
inhibition, that gating, that is not functioning as it should, that is creating that perception of frequencies without those external frequencies being present.
Mm-hmm. Mm-hmm.
Interesting. What is the function of gating and inhibition
Mm-hmm.
in the sensory system? So related
Mm-hmm.
to hearing specifically, but other senses as well. What is the purpose of that
Mm-hmm.
inhibitory function?
Yes. So the purpose is that your conscious higher order centers are not overwhelmed or flooded with information that is not necessary. We've also looked at this mechanism as it relates to people who have issues with speech perception and noise. Again, the theory being maybe the gating mechanism is not ideal in these individuals. And so noise is being allowed to reach conscious centers of the brain, which causes more interference and also draws heavily on cognitive resources to try to suppress it. And we found that to be the case, at least that a decreased gating ability is related to worse speech perception and noise in adults with normal hearing. So we do see that to be true. Gating in the neuropsych literature is often framed as, again, a survival mechanism if you're hunting in the wild. You want to be able to orient very quickly to new or novel auditory information. So if you're in the grasslands and you hear the grass rustling, you don't want to be paying attention to that because it's ongoing and it's non-threatening. But if you hear a twig break, you definitely want to quickly pick that up and be able to pay attention to it. So it seems to be, or is thought of as, part of that survival mechanism. And now is just an issue in communication, I would say, and cognitive processing as well, but could be involved in these auditory perceptions that aren't typical.
Interesting. Is there any evidence or any studies that look at this phenomenon in different cultures that have different
Hmm.
levels of exposure to sound, to
That's
different kinds
such
of sounds and
that's
media?
such a good question. That was a similar question was raised at this meeting I was just at, where we were talking about a different disorder called hyperacusis, which is sensitivity to the level of sound, and how loud it is. And one of the researchers was visiting family in India, which is a very loud place. And this is anecdotal. She was just asking, or, people and clinicians, is hyperacusis an issue there? And it doesn't seem to be as much of a problem because the expectation isn't quiet. It's loud, sound and noise all the time. So I do think there could be a cultural effect or maybe an expectation effect of what you expect to hear and what you don't expect to hear. So there's a lot of people who have tinnitus who are not bothered by it.
Mm-hmm.
And so if you're able to perceive a signal or sound, we call that tinnitus. But Dirk de Ritter just coined the term tinnitus disorder if it's bothersome. And so there seems to be this fallout where some people are fine with it and some people are not. And I've heard a couple accounts of people with tinnitus who were surprised to find out that no one else had it, or that it wasn't normal. They just assumed everybody hears this.
Mm-hmm.
Some kids who develop it think that, and you don't find out till much later. And so that's interesting as well, whether or not you think it's always there or should be there or not.
Is there a challenge with, and I imagine this is with many different disorders, is there a challenge in communicating exactly what you're hearing when people come in and report that they have tinnitus? Like, so I have tinnitus, and for the most part, it doesn't bother me. But if it's really quiet late at night, laying there, and I can really pick up on the different frequencies that are going there. So I wouldn't say that it's bothersome for me, but as an audio researcher and as a sound researcher, I can describe it. Is there a problem with people being able to describe exactly what they're experiencing, and how does that factor into research where you're doing something like an EEG and maybe tinnitus is not what they're experiencing?
It's very difficult. We do know the field is very aware that the approaches we use to measure tinnitus do not correlate or correspond to how bothersome it is, how loud it is, or how severe it is. So, what people might encounter in an audiology office for a tinnitus assessment is they fill out questionnaires, we need those absolutely. And then they might go through a frequency matching paradigm to try to match what it sounds like. And the problem with that is people who have tinnitus don't always have a tonal tinnitus, or it might be, broadband. It might include many frequencies. It can change, it can fluctuate. And so one day it might be at 6,000 kilohertz, and the other day it might be at 10,000. And so there's a lot of issues with reliability and validity with that. And a paper came out, I think, in JAMA or something similar in 2014, saying that it was not recommended to do this type of assessment clinically. Now, in research, it is recommended because we have to have some psychoacoustic measure of what people are hearing. But again, it is not ideal, and many researchers are trying to develop an objective measure using EEG because that's going to be really quick clinical translation. It can be very quiet. fMRI is very loud and expensive, and EEG is more cost effective in that sense. But it's very difficult. It's also something that we have found very frustrating in our clinic at UT Speech and Hearing Center. Is a significant part of our patient population is Spanish speaking. And we have had native student clinician speakers and clinical faculty try to help during tinnitus assessment to give instructions, try to really quantify or qualify what they're hearing. And it's just lost in translation. It's very, very difficult. And so that's been a big challenge, and something that I hope to work on in the future is how to bridge that language gap and then also provide intervention for this population because there isn't any Spanish-based tinnitus intervention.
Interesting.
Mm-hmm.
I can imagine even amongst English-speaking colleagues,
Mm-hmm.
I've noticed this, that once you start talking audio terms,
Mm-hmm.
it's like, oh, you're speaking a different
Right.
language. I don't know what you're
Yeah.
talking about.
Yeah, it's a
And
problem.
so having that terminology, that basis
Mm-hmm.
for conversation in other languages, in this case,
Mm-hmm.
your Spanish-speaking population, has got to be quite the challenge,
Yeah.
because it's not only are you speaking a different language, literally, there's that figurative speaking a different language. You start using terms that people just don't use in their everyday conversations, and so it's like, I don't understand what that means.
Mm-hmm.
You ask me what frequency I hear, or something like
Mm-hmm.
that.
Mm-hmm.
Interesting.
Mm-hmm.
Interesting. I'm really interested in this EEG research. With the EEG, are you able to map that perception on the EEG when you do correctly identify that it's tinnitus, and whether it's
Mm-hmm.
tonal or atonal, or whatever the situation is there mapping that correlates to that perception?
Right. So there's been a lot of work that has been able to find or identify neural networks in the cortex that correspond to tinnitus loudness and tinnitus distress, and those are different.
Mm-hmm.
So we do see that in the literature. As far as I know, I don't think it's possible to, like, let's say, identify an oscillation in the brain that represents the tinnitus tone
Mm-hmm.
and be able to map that. I don't think we've been able to do that. There's plenty of work looking at frequency based EEG analysis, looking at these oscillations, alpha, delta, all that. And we do find different oscillations reflecting or correlating with tinnitus aspects or characteristics. But I don't think we could say that's the tinnitus.
Yeah.
That's the perception of the tone in the brain. I don't think we could do that. No.
With the research related to inhibition and excitation, and
Mhm,
you were saying earlier about it possibly being, something with the
mhm,
gating, or the inhibition is not functioning because the
mhm.
excitation is not functioning, but then you've got excitation on different neurons that are not being inhibited. Does the EEG show the excitation and the inhibition differently, and are you able to sort of see
Mhm,
the data there, and kind of
mhm.
see what's going on?
So in the classical gating paradigm, we're not able to look at both excitation and inhibition. We're only looking at that amplitude difference to
Hmm.
those tones, and then we can quantify that amplitude difference and then say, okay, if you have a reduction in amplitude of about half, a ratio value, then you're gating.
Hmm.
But if it's higher than that, probably not if it's 1-to-1. But if we look at the frequency based EEG, we can look at oscillations that are reflective of inhibition and oscillations that are reflective of excitation simultaneously. And we do see those fluctuate in a complementary fashion. So gamma, which people associate more with excitation, excitatory processing signals, will tend to increase when these lower level oscillations decrease.
Hmm.
Then they're thought to be reflective of inhibition. So that's going to be your theta range of oscillations. So we can look at those simultaneously in things like resting EEG. So just having a person sit quietly with no stimulus at all, and we just record their brain activity at rest. And so we can look at just those oscillations, and are they related to any aspects of the tinnitus percept at all? And there's a lot of work in that.
With this research, what are your long-term goals? Because it sounded like at the beginning, it's a lot of it is just an understanding of kind of what's
Right,
going on there. And
right,
then, and I'm not saying that that's not enough. I just asked the question,
right,
beyond that, what are
right.
other goals that you have related to that? Because I think an understanding is very important,
Mm-hmm,
especially from a neuroscience standpoint.
mm-hmm. That's a good question. I feel like my goals have changed in the last year after being involved in the clinic more. My dream would be to help create a battery of tests for the tinnitus patient that can look at the entire auditory or even not auditory central
Mhm.
nervous system, and that this battery could help pinpoint the areas in that nervous system, or the networks, I should say, that are causing the tinnitus percept in an individual. And I think it's going to be different for different people or different groups. I think it's going to be different for people, who have had noise exposure versus somebody who has age related hearing loss. So that would be my dream. My very ultimate dream would be to have a center where we research these different tests, or this battery of tests for individuals, and in real time are able to implement those clinically, and then say what intervention best fits their tinnitus profile,
Mhm.
instead of just kind of blindly giving a type of intervention, which is, we don't blindly do that, I would say, but it's not great. Yeah, so just being able to offer personalized, targeted intervention while we're doing just simultaneous research and clinical application, because it's been really, really hard to see the status of clinic services for tinnitus. It's really disheartening. I mean, people are still telling patients there's nothing we can do for
Mhm.
you, which is not true. That's not true at all. And so it's just, I don't understand, and this might be my own naivety, with how far research has come in tinnitus, why the clinical service has not moved.
Mhm.
I don't know what the answer is for that, or how to bridge that, but it is, and the clinicians are going to researchers and saying, what's new, what can we, like, they're being very proactive. And the best I can recommend right now is send them to a study at a university. That's,
Mhm.
I mean, yeah, it's very challenging situation.
It sounds like it, yeah. So I want to go back a little bit to talking about sort of the impact of hearing loss from a cognitive
Hmm.
standpoint. Oftentimes with my students, I would talk about, well, I do all kinds of fun things. You do that frequency test and
Yeah.
say, who can hear 20
Yep.
kilohertz? And then you don't play anything and you see who puts the hand up. But, we talk about like the cocktail party problem, right?
Hmm.
So it's such a complex issue. And as you were talking about gating and inhibition and sort of that cognitive load, I'm
Hmm.
really interested in that early adulthood or
Hmm.
later, even later adulthood hearing loss. And what is the impact cognitively for people who suffer from adult onset hearing loss or later stage hearing loss? And where's the research in that area going?
That's a very hot topic. So Frank Lynn was, I think, I don't want to misspeak, but I think he was the first to find this significant correlation between cognitive decline and hearing loss. And in that study, they controlled for, I don't, a ton of things. They controlled for multiple medical factors and age and gender. I mean, many things. And this relationship was very strong. And so that spurred a lot of research to see what was going on there. Why was that such a interesting relationship? And there's still a lot of work being done in that area, a lot. And I think his group just came out with another paper. They're doing a long-term study looking at those effects and whatnot. So we did a little study where we tested several adults who had no idea what their hearing was like. And so we were able to separate them into adults with clinically normal hearing and then adults who didn't know they had hearing loss until our study. And they had, a mild, moderate hearing loss. And we just had them listen to some sounds while they watched a silent movie. So they weren't doing anything. They were just processing sound passively. And what we found was that in the hearing loss group, sound that was normally processed in auditory cortical regions was now being processed in frontal cortex. So they still had a little bit of activation in auditory cortex, but it had mainly moved to frontal cortex. So that resource had taken on the load of processing low level sound. So the sound they were hearing was a ba syllable. So not even interesting. And frontal cortex is highly known for executive function. So attention, memory, decision making, analysis, everything. And so our theory was if you're using these higher order cognitive regions to process sound that is not complex or in a complex environment, you're using resources that should be reserved for those types of stimuli. And that indicates increased cognitive load because you're already starting to pull on those areas when you shouldn't be. And so that was our theory. And some people might say, well, why has processing moved to frontal cortex? And again, we think a lot of it might be spurred by this visual reorganization. So visual system is taking from auditory areas. And so now frontal is taking over for auditory when it shouldn't be. And Dr. Sharma has written a few review papers on that that nicely summarizes that model. But it's a very strong relationship. It's very complicated, I think. There's some other factors that have been identified as probably being important in the hearing loss cognitive decline relationship. One of those being depression, one of those being social isolation. And I've seen that with my father and my husband's grandfather. When they couldn't hear at the dinner table, they just did not become involved. Yeah. They didn't engage. And then they got their hearing aids, and all of a sudden they were talking and they were engaged, and that hadn't been the case. So it's going to involve those things as well.
Are there implications or concerns as our environments get increasingly louder and as media consumption increases, and I would say both in terms of visual media and auditory media? As we know, hearables are a big thing. Everyone has the little wireless headphones in all the time, and people spend a lot of time with visual stimuli as well. Has there been any concern raised that this potential hearing loss or this recruiting of different areas could lead to some cognitive issues earlier in life for people that are experiencing hearing loss due to media environment and those sorts of things?
Right. So in that study that you mentioned with the single-sided deafness and the cochlear implant, that girl was 10 and she had started to lose her hearing. I don't know. It was a gradual loss over several years. And again, this is a case study. She was reported to struggle in school before this, and we showed visual reorganization with her and frontal processing of sound. And then after her implant, those reorganizations or reallocations reverted, and she was great and not having as much fatigue. So we call that listening fatigue when you're in a heavy, complex auditory environment and you just get tired. So I would say Scientifically it's a concern, but I don't think culturally it's a concern. There's mental health results coming out now saying that overstimulation is probably resulting in anxiety,
Mhm.
especially in our children. So being constantly on the phone and exposed to social media and having these comparisons and all these other things. But I don't think there's a clear answer for that relationship between overstimulation and hearing loss and cognition,
Mm.
at least in children. But we are seeing more young people come into the clinic with hearing loss. Or if they don't have clinical hearing loss, they're coming in with a lot of auditory complaints. I don't hear well in noise. And indeed, they
Mhm.
have a noise loss, even though their audiogram is okay. How do we help them? I
Yeah,
can't put
yeah.
a hearing aid on them.
Because it's not an amplitude problem, it's a processing,
Yeah.
frequency processing.
Mm-hmm. Yep.
Interesting. Yeah. It's interesting how, for so long, talk around hearing loss or protecting your hearing has always been, like
Mm-hmm.
protecting because you don't want to lose your hearing.
Mm-hmm.
But the conversation has been you don't want to lose your hearing because you want to be able to hear things.
Exactly.
And what I'm hearing now, no pun intended, is that it goes beyond just not being able to hear things, that there's now these other implications potentially to that hearing loss that aren't just
Yes.
about not being able to hear what somebody says or not being able to
Yes.
hear a sound. There's cognitive processing, and there's these other
Yes.
things that it's much more complex. As you began, the
Mm-hmm.
conversation with it is much more intertwined and much more complex than simply saying, well, you won't be able to hear somebody talk.
Exactly.
There's so much more to it that
Exactly.
needs to be a part of that conversation.
Mm-hmm. Indeed. When we counsel patients who come in to get a hearing test and they don't want amplification, I do make sure to let them know, the longer you wait, the worse it could be, and your brain's going to reorganize.
Mhm.
And that's also going to make it harder to go back in time to what your auditory resources were before. And we talk about that, and we talk about the visual piece, and that does seem to perk them up a little bit more and be more interested in helping their hearing. Because as you said, it's not just hearing, it's affecting you holistically. And then, as I briefly mentioned, there's the mental health aspect, which is
Mhm.
heavily tied to hearing. And we see with tinnitus, it's a huge factor. So it's a holistic issue. It's not just an auditory issue, no.
Thanks so much for
Sure.
joining us today and sharing just the really interesting work. We'll of course share your web link so that people
Yeah.
can follow up on the work that you're doing in your lab and the studies that you've been involved with. Do you have anything upcoming that you'll be publishing soon that we can look out for?
Yes. So we just had a paper accepted looking at actually recording the gating response in the presence of background noise, which was very hard to do.
Hmm.
So that's coming out in biology, the journal of biology, or it is out actually. And then my brilliant grad student, Lauren Ralston, a PhD student, she has her AUD, just published a paper looking at gating related networks in the brain in different degrees of tinnitus. Everybody had minimal tinnitus, but some had slightly worse, and how we're able to see brain changes at a very low entrance level to that perception where it's not severe. So she did that paper. And then Kenneth Morse, who's also doing some great gating work in tinnitus, and I are working on a paper together right now that will be in seminars in hearing.
All right. I look forward to seeing that.
Yeah.
I'm going to look up the one in biology now because that sounds really interesting. Thank you so much for
Sure.
sharing your knowledge and your insight with us today. And it's been a pleasure. I've really enjoyed the conversation, and
Same.
look forward to another one sometime in the future.
Yes.
All right. Thank you very much.
Thank
Have a good
you.
night.